All right, everyone, thank you so much for joining us on Did You Know, the ESCO HVAC show and podcast. So we've spent a lot of time discussing changes in technologies and refrigerant transitions that we're going through in the industry. I was over at Danfoss earlier. We were diving deeper into ways to manage heat exchange through a variety of different applications. And so today we're joined by Brian Dail, Application Engineer Manager for Danfoss. How are you, sir?
Doing great. Yeah, glad to be here.
So let's look at some things that have changed in our industry, and particularly in like our heat pump world. And I know I speak heat pumps all the time. I actually had one of our listeners catch me in the hallway earlier, and he said, you know, you can back off on the heat pumps a little bit because that seems like that's all that you've been talking about recently. And I said, well, we have to talk about heat pumps because we are now reintroducing heat pumps, especially higher performance heat pumps, in applications for every sector of the industry. So can you tell us a little bit about what area of that side of our industry you serve and the evolution that we're seeing?
Sure. So Danfoss serves heat pumps in a lot of different ways. There's just the standard ones that are a heat pump that would be in your regular standard AC unit. They work really great, especially in warmer climates, to replace just electric strip heat, give you a much higher COP.
Yeah.
But the goal is to try and use heat pumps in more places.
Yeah, more
areas, more applications, try and expand them up further. And one of the things we've been doing is working with more rooftop customers and more customers trying to make larger, better heat pumps that also operate at lower ambient conditions.
Yeah, because we think about like our traditional RTU systems. Like I worked on a lot of roofs. I've seen many, gas packs with straight AC, and always wondered, well, why don't we have an additional reversing valve and some controls for defrost? I mean, we're sitting up here on the roof. We've got a lot of sun. We actually have the prime opportunity to utilize a fairly open sky that is going to have potentially more heat exposure than we would sitting on the ground. And for the most part, we don't see a lot of heat pumps, especially in our light commercial and commercial RTU systems in the past.
Yeah, in the residential market, close to 40% of the HVAC units that are sold are heat pumps. In rooftops, it's more like 10%, 20%. Wow. The numbers are a little harder to find on that. It's not as easy, but that seems to be about how it is. So it is an area for improvement for the industry, because even if you want to keep that gas furnace on there, a heat pump can work great in your shoulder seasons, and it kind of depends on where you're located. Here in Florida, you could use a heat pump for all your heating needs, and you'll never need the gas. But if you're further north, you can use the heat pump in the shoulder seasons and the gas in the deep winter. But there's also cold climate heat pumps as well that can allow people to use heating all heating season all through the winter.
Yeah, absolutely. So when we start looking at what those potential heat pump applications are, it really changes our perspective, because we've got jurisdictions around the country that are looking at installations saying, you know what, you're actually not going to be running gas lines to this building now. And we go, wait a minute, what are we going to do on a commercial building? How are we going to supply heat and cooling for these structures, besides putting chiller plants and besides looking at those as options? Well, if we start looking at heat pump applications, it really broadens the scope of our projects when we can implement heat pumps and even high-performance heat pumps into these commercial applications.
Yeah, so it becomes a challenge to implement heat pumps in colder climates, but it absolutely can be done. The challenge comes from the fact that as it gets colder, you need a greater heating capacity.
You bet.
So the way I think of it is, if you've got a air conditioning system that's designed to take it from being 100 degrees outside to 70 indoor, that'll also work really great in a reversible heat pump to take you from 40 degrees up to 70 degrees inside a building.
Sure.
So, excellent for Florida. How many days does Florida get below 40? Almost never. So, great solution there. As you get further north, you're going to need more capacity in the heating season than you would in cooling. So that becomes a challenge. How do you address that? You can use more systems, and you'll have more kick-on for heating during the winter season, and you'll have fewer systems in operation for cooling during the summer. Also, there are systems that can have variable capacity, and that could come from having multiple compressors that stage on and off. It could come from variable speed compressors, where you're now running full speed during the winter, and you're running at lower speeds during the summer.
Okay. Do we have any commercial HVAC contractors with us today? Okay. All right. So this Maybe new information, may not. And if you have any questions along the way, let us know, because this is really an emerging market as we start looking for solutions for applying heat pumps in applications that haven't traditionally been the focus. And so when we look at all these solutions and we start focusing in on how heat pumps can provide those, what types of ambient temperatures are we starting to see for both traditional heat pump and things that are probably going to be used in things like vapor injection and alternative means to be able to get down to ultra low temperatures? What type of heating capacities are we seeing in some of these like commercial heat pump situations?
Yeah, so standard, fixed speed or non-vapor injected compressors, they can operate still really well down to about 17F outdoor temperatures.
Right.
Once you start getting your evaporator temperature below freezing, you have to defrost more often, which is a challenge to deal with.
You bet.
But even doing some occasional defrost, you can still get pretty good heating capacity down to, let's say, 17 degrees. And that's one of the testing conditions that's used in one of the AHR tests for commercial rooftops heat pump.
Okay.
And they can keep operating below that, but that's where you start to have to add more tricks. And one of the easy tricks is to add vapor injection to a compressor. And that vapor injection can allow you to operate down lower. We have compressors coming out that can operate down at minus 35, minus 40 evaporator temperatures, which means they will be able to produce heat for you even at these extremely low conditions.
Okay, so for those in the audience that are not aware or don't completely understand what vapor injection does for the refrigeration system, can you help us understand a little bit about how vapor injection applies to a compressor and what it actually affects?
Sure. So let's start with how would you identify that you've got a vapor injection compressor if you're going to go work on a unit.
Right.
You're used to seeing the suction input and the discharge outlet.
Got 2 lines?
Yep. Mm-hmm. But if there's a third line going into it, might be a little confusing as to why. That's almost definitely going to be your vapor injection line. There's other ports on a compressor for, sometimes there's a sight glass or a tap for, where you take a pressure reading or drain oil.
Right.
But generally, if you see a third refrigeration line, almost definitely that's your vapor injection port. And what that's doing is it's injecting gas somewhere. If you've got a scroll compressor, somewhere in the middle of that scroll cycle. And I'm using my hands on a podcast.
Absolutely.
Not the best way
we got video. We'll capture
yes,
this.
It's good for the video. It's not great for the audio.
In the middle of the compression cycle, and that's the most important thing to understand. That it took me a minute to understand that philosophy. Like if I just take higher pressure discharge temperature, discharge vapor, and I introduce it into the low side of my compression, I'm just simply going to raise the low side pressure. I'm really not going to be benefiting any of the actual work, that heat of compression. But if I introduce it into the middle of that pumping cycle, after I have closed off my suction and before I have opened onto the discharge side of it, I can introduce refrigerant into the middle of that compression cycle and actually affect some of that compression. It's a very interesting fact. So what happens as we introduce vapor into that cycle? Like, what are the outcomes?
Yeah, so a good way to think about it is the bigger difference in pressures you have between your low side and your high side. So the lower your evaporator temperature is, the higher your condensing temperature is, the more work that compressor is going to have to do to compress the gas. It kind of just intuitively makes sense. Bigger raise in pressure, more work has to be done.
Okay.
So if you've got vapor injection, you're now not having to put all of that refrigerant in at the lowest part. You're getting to do some of that injection at a higher pressure. So some of that refrigerant is flowing through at a higher pressure. So it's an easier way to do that compression. If someone's ever worked on a supermarket, this is very analogous to when you're using a medium temperature rack to subcool your low temperature rack.
Sure.
You're having that more efficient medium temperature rack do more of the work for that low temperature part of the system. And that's a good analogy if you're familiar with supermarket refrigeration.
Okay. And so we're going to we're increasing some of that compression ratio. And so I imagine we're probably increasing the discharge temperature a little as well in that cycle.
So it can potentially increase the discharge temperatures. The use of vapor injection is good for improving your efficiency. It both improves your capacity. It improves your capacity on the same system, which boosts your efficiency.
You bet.
And then it can sometimes start to increase your discharge temperatures. And you can control that because that vapor injection, what's the superheat of that vapor that you're injecting? If you inject vapor that's at a lower superheat, you'll have lower discharge temperatures.
Gotcha.
And as the ambient temperatures start to get lower and lower and your condensing temperatures get higher, you can start to reach a point where discharge line temperatures just get too high, even with the vapor injection, But that's when our compressors can take what we call wet injection. Wet injection is where you're having superheated vapor come into that intermediate port, into
Right.
that injection port.
Middle of the compression cycle.
Wet injection is where now you get to 0 degrees superheat, and
Oh,
you're
really?
actually putting saturated refrigerant right into the
Wow.
scroll itself. And once you're doing that, it's no longer providing you with an efficiency benefit, but it is keeping that scroll
Cooling.
cooler, which
Yeah.
will allow you to still produce heat even at those very low ambient conditions. It'll allow that compressor to still stay running without breaking down.
It's an intriguing philosophy because in most refrigeration training, we're always looking at we never want liquid in our vapor compression cycle. And
Yep.
now we're actually intentionally introducing a small amount of liquid, I imagine, to be able to help cool that compressor to maintain its function so that it can continue to work in these lower ambient temperatures. Because when we start getting down to like minus 35, minus 40, that compressor is really doing a lot of work. That original suction pressure is going to be so low, we have to do something to be able to raise those pressures to consequently raise those temperatures. Okay. All right. So, yes, question, Robert. Great question. I'm glad you asked that. Yeah. So let's think about that from a refrigeration cycle. Where would you get a low pressure vapor from? Okay. So, Brian?
Yeah, so we call it a refrigerant side economizer. And we have to specify refrigerant side because when people hear economizer, especially with rooftops, they oftentimes think like an air side one. You're going to bring in some outdoor
Right.
air. Well, anyway,
Correct.
we're talking about refrigerant side economizer. So what you do is you have a tee off of your standard liquid line, the liquid line leaving your condenser. You put a expansion device after that, and that expansion device is going to feed a heat exchanger. And most commonly, you'll see a braze plate heat exchanger, and you'll use that braze plate heat exchanger to subcool your same liquid line, and then the vapor that you're using to subcool that liquid line further, that is the vapor that you will inject into the intermediate stage.
On the other, yes.
Yep.
Exactly. So you'll see two metering devices there.
The other side of that heat exchanger is in the intermediate port. So one side is all liquid line, one side is teed off of the liquid line to an expansion device, and then vapor leaving that braze plate to enter the side of the compressor.
Yeah, so we are absolutely coming off from our liquid line through another metering device and reintroducing that reduced pressure back into the...
The models I have seen out on the show floor have always been EXVs. There's no reason you couldn't use a different device. I would probably want something smarter. That's always what I have seen.
Electronic.
You could use a TXV. I kind of like to experiment with a customer that's interested in using a TXV there just because it would be fun to play with it, see how well it performs.
Yes.
But that mass flow can vary a lot. The pressures can vary a lot. It's nice to use an EXV because it can control over a very wide range because you're going to have a lot of different mass flows throughout the different situations where that compressor might operate. So the EEV is going to be the most precise and accurate, but I see no reason why in the future you might not be able to see one that's got a TXV, a piston, or some sort of fixed orifice. I don't know. It gives you so little modulation.
Right.
That one's a stretch to me. I don't want to say never, but I don't think that's a great idea.
No, and the ones that I've seen the most have been electronic, and reason being, so say we're down on those very, very low temperatures, minus 35, minus 40. It's hard to imagine a refrigeration cycle working in that low of temperature, let alone a heat pump that's extracting heat out of the air. So in those ultra low temperatures is where we need the most vapor injection, and that's where our electronic expansion valve is going to be open more. We're going to be throttling more into that cavity. But think about that as that ambient outdoor temperature starts rising. Because remember, we're utilizing some of our liquid refrigerant through a secondary cooling process. As that ambient temperature starts rising, we don't need the vapor injection as much. So we can actually start reducing that vapor injection until we get to a point that the compressor is back to full efficiency, and we can close it off. Yeah, through the control. It's going to modulate that EEV.
Yeah, you'll put a pressure transducer and a temperature sensor at the outlet of that heat exchanger to measure what your superheat is.
Yeah. So it was very intriguing when I first started looking at this principle. Makes a lot of sense, right? If we're even talking in a standard air conditioning scenario, if we wanted to make a compressor more efficient, we need to cool it when it's working its hardest. So in the opposite side, when we're looking at heating, that's exactly what we're doing. So we're trying to allow that compressor to operate at its maximum potential. We know that it's going to be working hard, and what better way to assist it when it's working hard? Just cool her down just a little bit and give it some additional compression. And so that's what we're seeing in this evolution of, we'll hear a variety of terms. You hear enhanced vapor injection, straight vapor injection. And so we're going to be seeing that technology in a variety of products, I'm going to imagine.
Absolutely, yeah. I work a lot with our Danfoss's rooftop customers, but it's also a great solution to put into a chiller where you're maybe trying to use that chiller not to produce cold water, but to produce hot water and maybe replace a boiler, or depending on the process, at least preheat the water, and then the boiler can get it the rest of the way up. Because there's a lot of things you can do to reduce your energy consumption, get heat pumps to work a lot of the time for you, and you use natural gas or some sort of fossil fuel to finish off the rest of it, just depending on what the process is. With 454B, no matter what the evaporator temperature is, it's going to be hard to get water much above 140 F, and sometimes that's great for heating a building, but sometimes you need warmer temperatures than that. And a lot of boilers were designed to spit out 160, 180 F water, and so a 454B vapor compression cycle is going to struggle to get those temperatures. So you have to either go with alternate refrigerants that can have higher condensing temperatures, or you take what you get from the heat pump and you finish off the rest with natural gas.
Absolutely.
So you're taking your water from 70 up to 140, and then the rest of the way can be done by a boiler instead of having the boiler have to take you the whole way through it. And you still get to do a lot of energy savings that way, a lot of reduction in your fossil fuel usage that way. But you can't cut it out entirely.
No, absolutely. One of the prime examples that really made me think about the potential of using heat pumps, especially in larger applications like in our commercial buildings and structures, we would always look at what is our two energy sources that we have for a larger building. We have a chiller to cool water, and we have a boiler to heat water. Well, what if we're just doing an adaptation of our chiller, and we now put in a heat pump style chiller and allow that heat pump to do most of the preheating of our water at a very high coefficient of performance, and then use that additional gas boiler to raise that final product. So you're allowing that chiller to now become a heat pump chiller that is going to be warming our water instead of cooling it. Same piece of appliance, now we're just going to be able to use it for multifunction.
Yeah, and heat pumps are going to be able to give you a great coefficient of performance. Even the best furnace, it's 98% efficient. That means it's got a COP of 0.98.
Yeah.
And we've sold compressors to some of our customers that produce heat pumps that are making hot water, and they're getting COPs of 5 or 6. And natural gas is usually pretty cheap in this country, but if you can get a COP better than 3.4, then that heat pump is paying for itself. And even if you have a system where half the year it's way better than 3.4, half the year it's worse, you can break even or even better depending on how the math works out for how much of the year you're getting these really high COPs versus lower ones as the outdoor temperature drops.
Are you seeing an increase in demand from our consumers that are replacing chillers and are now looking at heat pump style chillers?
Absolutely. We're definitely seeing a big drive in the market of heat pump chillers.
Yeah.
And like I said before, they're used in different ways. Sometimes it's the preheating model, like you said, like, hey, the heat pump will do a lot of the work, the boiler will finish it off. Sometimes it's being used to entirely replace the boiler. It sort of depends on the area, the climate, the local regulations. New York City is trying to get away from natural gas in new installs, so that's definitely an example of a location where there's a big drive for heat pumps to replace boilers. But in all parts of the country, especially if you're just going to go with the preheat option, it's a easy step to kind of work your way towards more electric heating.
Yeah, because exactly, even in our residential sector, it's difficult to have a consumer who is used to using an air conditioning system and a gas furnace to convince them it's heat pump time. It's time for a transition to a heat pump. So it gives us that opportunity to focus on a heat pump for a primary performance and still utilizing that gas furnace. So it's a dual fuel application. It's typically what we call it. But we don't always think about that as the commercial side, having a dual fuel option as well. And that's exactly what we're talking about. The ability to have a heat pump that can do work for you, but to also use that gas-fired boiler for, especially in those ultra low temperatures. We may just want to go ahead and shut off that heat pump and then transition over to our boiler only, or we're going to be able to use that heat pump. That's exactly it. Robert, I'm so glad you said that. So when we start talking about why don't we do that, it's really a great conversation. It's because we've been building chillers for decades. And now we're finally going, wait a minute, if we're using a piece of equipment outside to manage the temperature of water, why don't we use technology to manage it for both heating and for cooling? And that's what we're starting to do. That's why we're having this conversation, because in the past it's not really been a common conversation, because if we look at heat pumps from 30 years ago, they weren't really that efficient. But technology has really changed the way that we can remove heat from the outside air and use it for purposes of any type. Because remember, whether we are in H, in V, in A, in C, or in R, we are all in the business of moving heat, right? That's all we do is move heat. And so we're trying to challenge the industry to think about moving heat from a different perspective and utilizing heat pumps for that, for a variety of different applications. I like it. Sounds great. So when we talk about product lines, what product lines have we implemented heat pumps into?
What product lines? Residential split systems, rooftop units, chillers. I can't think of a product line where they haven't been implemented in. Only maybe in your R example, you just went HVACR. Sure. R. I mean, they're
a cooler. It's a cooler.
Yeah. But even there,
Yeah, exactly.
You say that though. If you're in a walk-in, you could instead of running electric.
Oh boy. You missed the conversation we had with Danfoss earlier, exactly talking about that. It's like we're in the business of moving heat. If I'm pulling heat from a place, where can I put it?
Yep. In a refrigeration application, the only reason to there's no reason to not try and find a way to reuse that heat. So Absolutely. If you have a walk-in that's going to be making a box cold year round, you can always use that extra heat to preheat your hot water.
Sure.
And that's a situation where it's probably. Yeah. Oh, absolutely. Yeah. So sure. That's something supermarkets do, and it's something that really any food installation could use, because every restaurant's going to use hot water. I think you're required by code. That's not my area of expertise, but I think you have to wash your hands with hot water, right? So you probably have to always have hot water. So any place with a walk-in, there's a potential there to use some of that heat to at least preheat your hot water. Oh, absolutely, sure, because that's free energy. Absolutely. Instead of blowing it off to the outside, you put it in the water, and then your boiler can get it the rest of the way there. Might even be certain times of the year where it can do all the heating for you. It would have to depend on the system.
You had mentioned in that residential application of heat pumps, I like to be able to help people understand, since we went through that concept of vapor injection, does it make sense on a large scale how we could do that process to cool a compressor now? So as you're walking around the AHR Expo, have you noticed residential heat pumps that work at ultra low temperatures? Have you thought about why? Okay, I'm so glad you're here with us today. So when we talked about it, like vapor injection on a large-scale commercial heat pump, and we understand now that we can allow that thing to operate in very, very low temperatures, what if we simply took high-performance heat pumps that we are already manufacturing and introduce vapor injection into those compressors? So that's really what we're doing. So the importance of understanding vapor injection in the refrigeration cycle is going to be crucial for all heat pumps that we recognize going forward, because as we push any heat pump to its maximum capabilities, as we push the compressor envelope to its limits, we have to understand that we're going to introduce new technologies to help make that more efficient and get it back into a comfortable operating range. So that enhanced vapor injection that we just applied to these larger heat pump systems is exactly what we'll do in that residential heat pump application. So it's very important for us to understand the concept, so that when we're introduced to these chiller heat pumps that are operating in very, very low temperatures, our commercial heat pumps that are operating in very, very low temperatures, we already know how a heat pump works. the most important part is to understand that little piece and the new technologies maybe that we don't understand. So when we put those two pieces together, now we're going to be introduced to a new product. We already knew this much. We've now learned this much, and we have a complete understanding of the operation. Because I see heat pumps moving into all sectors at a fairly rapid pace. At Danfoss, have you been looking at heat pumps as a primary market for your compressors going forward?
Primary, I would say yes, because we have the PSH line of compressors, which is a compressor that's entirely done with vapor injection or liquid injection. So that is a product that is entirely aimed at heat pumps.
Oh, wow.
Our other compressors that are standard fixed speed with non-injection can certainly be used in that application too, but the vapor injection gives a extra efficiency boost. It increases the areas in which it can be a high-performing heat pump.
Okay. And so what capacities does Danfoss manufacture compressors that can be used in heat pumps?
So we have compressors that can be used in heat pumps from as low as 3 tons all the way up to 40 tons and in just scrolls. And then we've also got our TurboCore line of compressors, which are oil-free centrifugal compressors that are... I'm not the best TurboCore guy, but they're usually 100-ton compressors that they get paired together in multiples to get even higher than that. So the TurboCores are definitely used in large systems. I know there are some smaller ones that are more like 80 tons. What was that? CentralVac, I think that's a brand name for one of our competitors, but it might also be just the name that they go with for the chiller that maybe does use our compressor. We call it the TurboCore compressor. Yeah.
Are there refrigerants that work better in heat pump scenarios than others as we get into these commercial applications?
Yeah, so the question of what refrigerant is going to work better than others, it sort of depends on what you're going for.
The application.
Yeah, so as you walk around the show, if you're looking at like domestic hot water heat pumps, and when domestic, I mean like potable, for sanitation purposes. There, you have to get a high hot water temperature. You can't take 110 degrees and just deal with it. You have to get up to 140 or higher so that it can be considered sanitary. So there, you might need a refrigerant that's going to allow you to have a higher condensing temperature, and that's where refrigerants that are, let's say, alternatives to 134A fit in well. So like 513A, 515B, because those allow you to get a higher condensing temperature. And I know we're being recorded here, but I'm also going to be this is going to be on a podcast. So maybe I should do more. I should describe what I'm doing with my hands. Yeah, so I'm describing the pH diagram. Refrigerants that are 134A or similar, like 513A, they have a higher curve there, so you can get to higher condensing temperatures before you go off the pH diagram. Okay. So in those types of applications, something like 513A is better because you need those higher condensing temperatures. However, if your goal is efficiency and maybe the higher temperatures aren't the most important thing is efficiency, using 454B or R32 would be the best because they're the higher density refrigerants. You can get higher mass flow out of smaller compressors, do it with less energy, and those are going to be the most efficient for comfort heating type purposes because whether it's a air-to-air system, if it's air-to-air and you've got a 100-degree condensing temperature, you can produce warm enough air to heat a building. If you're heating water, you need to get higher than that, but it sort of depends on how your building's designed, how your heat exchangers are set up. 120-degree hot water can heat a building nicely if your heat exchangers that are throughout the building are set up to handle those lower water temperatures. Yep. The grandma's radiator at her house that's meant to have the high hot water temperatures that are going to scald you, those ones might not work as well with 120.
BTUs with cooler water, right?
Yeah, exactly. Yeah.
No, that's fantastic. Makes a lot of sense. So sometimes it's a matter of looking at the design, the load conditions for the structure, working with a specialist from Danfoss to kind of evaluate the system that you have to look at what those options are. So if you're reducing that outlet water temperature, maybe we need to look at the design, the system capacity as overall to find the best fit for it.
Exactly, yeah. It's important to take a step back and try and think, what am I trying to do here? What's my ultimate goal? Is it to get rid of all natural gas? Is it to get really high hot water temperature? There's all sorts of different things that you can have in mind with your goal when switching to a heat pump.
Excellent.
Yeah.
All right, any questions? Anyone have any additional topics that you'd like for us to cover while we're moving into the new generations of heat pumps for residential, commercial, and potentially even industrial applications? Yes. In one product, do you see any of those types of applications?
Yeah. I mean, agriculture is definitely an area where heat pumps can come into play, where you're using it to heat hot water, and depending on the season, you also can cool other parts of a building. And now you're getting maximum efficiency because everything that you're doing has a use. There's no waste heat, there's no waste cooling. Everything's got a purpose.
Absolutely.
Yeah.
Anybody else? All right, Brian, well, I sure appreciate you hanging out with us today. We're glad
Absolutely.
everyone came here to learn a little bit more about the ways that the industry is moving into a new era of technology and how technology has been implemented into compressors at Danfoss to provide maximum efficiency. What are ways that we can connect with Danfoss to learn more about the products that you provide?
And we have a website, we've had a website for, I'm sure, more than 25 years,
Yeah.
so that's an easy way.
Sure.
From there, get to our website, you can get into the ways to contact all of us, various different ways. Yeah, I'll go with that. Let's go with the website. How's that sound?
There you go.
Yeah.
All right. Thank you, everybody, for joining us today.
All right. Thank you.
Appreciate it.
Yeah.